I can't put that on there. No.
Let's get started. So today we are going to be deriving transfer functions, general formula, and also understand what's involved there. I will start by rewriting a dictionary, which on one side we have function of time, on the other side we have Laplace transform of the function. Bar on top always means Laplace transform. I will not always put in parentheses of S. Careful, the transfer functions are functions of S, but they are not Laplace transforms. Okay? They have an interpretation of Laplace transform. I think it will be confusing to talk about it. So, remember, this one has then I will not write everything last time. I'll just write the ones we're going to be using today. Very important, Laplace transform of the derivative of function of time is S times the Laplace transform of the function without the derivative minus, not the Laplace transform of the function, the actual function at time 0. And I'll also put the time delay expression. If I have a function that is 0 for an interval, and of course what matters is 0 between 0 and that time, because only positive times are involved in the Laplace transform. And for times greater or equal to d, it is some function delay. That function can be expressed in terms of the Laplace transform of h undelayed. H bar of s is the Laplace transform of h undelayed, the Laplace of h of t times e to the minus ds. Okay, so we'll leave this part of the dictionary. And there will be an important implied assumption. And haven't seen this done well at all in text. Usually texts don't even mention it, just assume without justification. And I think my best way for introducing that is through a very simple example. And I'm not going to repeat the setup of the example. I'll just write the equations that we had at the end of Monday's class. And the model that we had so step one, our model was this constant volume, constant temperature, constant density, CSTR, with A goes to products. That's it. So the result of step one was that dCA dt is F over V times CAF minus F over V CA minus KCA, and the measurement equation. And again, here I'm not putting of t. Everything here, every variable, if you want, you can put parentheses of t, parentheses of t, parentheses of t. If everything is clear, everything t, I'm not bothering to put it. But if in the equation I have at two different times, as I have in the measurement equation, then I'm putting the time dependent. Step two, was the nominal steady state. And we're given that Ca F nominal was 0.2 moles per liter, and we're calculating from a 90% conversion that Ca naught is 0.02 moles per liter. And V is a parameter constant. V was 100 liter. That's not nominal steady state. And K is a parameter, 0.1 minutes inverse. And with that, setting this equals 0, putting F naught, Ca F naught, Ca naught. We calculated what F naught is. So setting VCA dt at nominal steady state equals 0. We found that F naught was 1.11 liters per minute. And of course, the measurement equation is y naught equals Ca naught, which is of course 0.02 moles per liter. So that's where we were. Any questions? Okay. So the key thing about the transfer function model is that we do not have the state variables. Don't think about this very simple example that I have only one state variable Ca. Think of the distillation column when I have 96 state variables. Okay? What is controller design? We are designing the manipulated input, how it should change in response to measurements of y, the measured output. So you can understand that if you have to try to get all the x's, etc., that's a mess. You have to go through the x's. An input-output model is a model that eliminates the x's. There is no general methodology for getting an input-output model for nonlinear systems. You can get approximate ones, but again, you're doing linearization anyway if you do approximate ones. But for a linear system, and that's why we have done the linear approximation, there is certainly no question about it, general methodology for getting it, and a very convenient way is the Laplace transform. And what allows us to eliminate the state variables is this entry tradition. Using this property, the differential equation part of the model becomes an algebraic expression for the Laplace transforms of the state variables. And it's a linear algebraic equation. We know how we can solve analytically systems of linear equations. So we can express the Laplace transform of the state variables as a function of Laplace transforms of the inputs manipulated in disturbances. And so we can plug it into the measurement equation and get directly a relation between Laplace transform of measured output and inputs. That's basically what is involved here. But there will be a critical assumption made. What I refer to as the implied assumption because it's normally not even mentioned. So I will use this system for it. It has a standard class notation with the system that I have here. X is x1, x Ca, right? That's the only state variable that I have. So U is F, and D is D1, which is Ca. These are the variables. So let's calculate step 3, the approximate linear system. Really a lot of stuff over here, I'm being sarcastic. Anyway, so step 3. Oh, okay, what's this equation? Let's write. So what do we have? We have x1 dot equals, that function is u v is 100, CAF is d1 minus d over 100 x1 minus 0.1 x1. This is what this model is in standard Lewis notation. Okay. And of course, y is x1 dA. Okay, I just rewrote the model plus one. So, in step 3, trying to fit everything in this board so I have the other 3 boards available. Linearization. What do we need to do? What do I do in the linearization step?
Derivatives of stuff.
Well, Herzenberger, maybe Thomas, maybe
You say-
Juan. But it's basically calculating A, B, gamma, and C transport, right? That's what it is. So let's calculate the A matrix. What's the size of the A matrix?
1 by 1.
1 by 1, exactly. I have only one state variable. So the A matrix, which is 1 by 1, is simply A11, which is the partial of our only F with respect to our only state variable at the nominal steady state. So what's that?
So d1 divided by 100 minus x1 divided by.
This is my F1, right? It's
Yeah.
going to be minus, there's no x1 here, minus u naught over 100 minus 0.1. Which makes u naught is 1.11. What did I do? Hold it. Oh, I think I made a mistake in writing what F naught is. I think F naught is point. No? Wait a minute. Oh! I did something wrong here. Because I should be, oh, it's over 100, okay. Everything's right. Somehow it's dividing by 10. And that was not really the right answer. So this is minus 0.0111 minus 0.1, so that's minus 0.111. I'm not writing the zero since I don't have space. Okay. The B vector is also 1 by 1. What's the partial of F with respect to F1? With respect to the manipulated input at the nominal steady state? I have you here and I have you here, right? Felix.
I'm sorry, what's the meaning of that X between brackets?
Matrix.
It's not an X, it's the size of the matrix. 1 by 1. 1 by 1.
Oh, I thought it was an X between brackets. Sorry.
It's the size of the matrix. Okay, that's what I said. It's not absolute value of X. 1 by 1. Here, I'll take it out. It's confusing, take it out.
No, it's okay. I'm good.
I was just putting the size. Right? And, oh, so that is u naught over 100, sorry, d1 naught over 100 minus x1 naught over 100. This is the only two places I have u. So that's 0.2 minus 0.02. So that's 0.18 over 100. So that makes 0.0018. And the gamma matrix is simply again gamma 1, 1, partial of f1 with respect to our only disturbance at nominal steady state. So d1 appears only here, so that's u naught over 100. So that's 0.011. So that's the result of step 3. I don't have space, I'm not going to work right away with this equation, but obviously G is x1 delayed. Partial G with respect to x1 delayed is 1.
CT is
So C transpose is simply 1 in this case. Okay? All right. So the result of step 3, so the approximate linear model memorizing deviation variables. So that's ax prime plus b u prime plus gamma d1 prime. I'll write the y prime, but we have the y prime at the least. Yeah, I'll write it. I'm not going to use it. Okay. So, I want to get a model that will not have any more x1 prime. So the way they can do it, in the Laplace domain, the differential equation becomes an algebraic equation. So I can solve for x1 prime bar. So let's use the dictionary. So dictionary then. So you Laplace transform an equation by Laplace transforming every term of that equation. Remember, Laplace transform is a linear operator. So if I have a Laplace transform of a sum of terms, that's equal to the sum of the Laplace transform of each term. Clear? So, we use the dictionary for, let's call this equation 1. So, we're going to Laplace transform equation 1. So, we're going to the dictionary and looking at its terms. Left hand side, do we have anything in the dictionary that looks like that?
That's a derivative?
Has a big square on it, right? The one I put the big square. Remember, dot on top is time derivative. x1 prime is a function of time. So that f in the dictionary is x1 prime in this case. So the derivative of x1 prime dt using the dictionary is going to be s times the Laplace transform of x.
You were doing so good.
Yes, yes. Oh, damn, this is not rich. See, someone save some of mine for oh, yeah. Actually, almost. So, x1 prime, but no, I have. Minus the function at time 0